Hello everyone, welcome to our chemistry class. Now आज का जो वीडियो लेक्चर है यहाँ पे हम लोग डिस्कस करेंगे द कंसेप्ट ऑफ वर्क डन इन्वॉल्विंग एन आइडियल गैस. So we will define this work done in terms of the pressure and the volume change. So starting with the work done, now we consider a cylinder containing 1 mole of an ideal gas. This cylinder containing 1 mole of an ideal gas is fitted with a frictionless piston so that it can easily slide down or up without any friction. Now on the piston, pressure acting on the piston is known as the external pressure due to external gas. Since we also have 1 mole of an ideal gas, so this ideal gas will also act pressure on the piston, and that pressure is defined as PI, ideal pressure, that is pressure due to internal ideal gas. Now depending on the values of external pressure, this piston will move downward or will move upward. If the external pressure is greater than internal pressure, this piston will move downward till the external pressure becomes equals to internal pressure. Or if the internal pressure is greater than external pressure, then the piston will move upward till both the values are equal. So depending on the external pressure, we can move downward or it can move upward. Now during the course of movement of this piston, the distance moved by the piston be L and the area of this surface area or the area of cross section of this cylinder be A. Then we define the pressure. Pressure P is defined as force per unit area. So therefore from this we define force as pressure into area of cross section. Then we define, now look at this, volume, change in volume, which is defined as V final minus V initial. Now this change in volume is equals to the area of cross section into the distance moved by the piston. This during the course of movement of this piston, this is the distance moved by the piston and this is the surface area. Then the change in pressure volume will be surface area into the distance moved by the piston. So we have this. This is A, this is B. Now we have to define the work done. So therefore work done is equals to force into the distance. So therefore look at this, force into distance. We have this, combining this one E and B, we define this force as pressure into area, that is defined as the force into L. Now look at this equation B, area into length, this is defined as change in volume. So therefore look at this, work done involving an ideal gas is defined as pressure into change in volume. Now here I am taking this pressure as external pressure as a limiting criteria because Based on the value of external pressure, we can move downward, it can move upward. If this is moving downward, that is always compression work. Surrounding is doing work on the system. If there is an external pressure is less than internal pressure, this will move upward. So there is expansion work. Expansion work means work is done by the system on the surrounding. So therefore we say this is P external into change in volume. So work done is equals to P external into change in volume. Now look at this. We define the convention of work as positive if surrounding is doing work on the system, work done on the system, that is work done on the system, that is P external is greater than P internal, that is compression work. If compression work means there is a decrease in volume, so volume decrease, work done should be positive. So to make the convention of work, the final expression of work done is written as minus P external into change in volume. So this is the final expression of work done involving ideal gas. These negative charge is to satisfy our sign convention of work, because nowhere in the derivation there is negative sign. So negative sign is to satisfy the sign convention of work done. So look at this. If external pressure is greater than internal pressure, if P external greater than P internal, work done is P external greater than P internal means volume is decreased, delta V is negative, so therefore work done is positive, that is compression. Work done on the system, that is what we call as compression work. If P external is less than P internal, then there is increase in volume. If volume is increased, then work done is negative. So volume be positive, work done will be negative. Work done negative means work done by the system. So if work is done by the system, that is what we call as expansion work. So we have work done by the system, work done on the system. Work done by the system, expansion work. Work done on the system, compression work. During compression, volume decreases. To make the work done positive, we have to use this negative sign. So during expansion, volume increases, so work is done by the system. So work done should be negative. To make this negative, again we have to use this sign convention. So this sign convention minus sign, this is just to satisfy the convention of sign. So whenever we use the work done involving ideal gas, we will use this expression. This work done is equal to minus P external into change in volume. So this is we define as pressure, volume, work. Now we define this work done in two different headings under isothermal process and the adiabatic process. So now let's go to the work done in isothermal process. work done in isothermal process. Work done in isothermal process. Now, for an isothermal process, as we know, delta T is equals to 0, means temperature remaining constant, so we say isothermal process. Now, from first law of thermodynamics, if delta T is 0, then delta U will also be 0 for an ideal case, as we have explained earlier. For an ideal case, U is a function of temperature only. If temperature remaining constant, delta U will also be 0. So therefore, from first law of thermodynamics, we have delta U is equals to Q plus work done. So therefore, this being 0, we have Q is equals to minus of work done. Or we can say minus of Q is equals to work done. So now we have to define the expression of this work done for an ideal gas in isothermal process. Now, for this, now look at this. Let's define isothermal reversible process. Reversible process. So a reversible process means the process which is very slow and the change is taking place in an infinite numbers of states. Slow step. So taking place very slowly. Change from initial to the final state is taking place in infinite numbers of states. That is very slow process. That is what we call as reversible process. Now, for this reversible process, now look at this. We define this work done, that is isothermal reversible. Isothermal and reversible. This is minus P external into change in volume, because being reversible, change in volume should be very small. So we represent this by P delta V. Sorry, P dV. Now, look at this. We can use this P external in external pressure is equals to pressure due to ideal gas plus minus some small change in pressure, because look at this, the compression work or the expansion work depends on the values of external pressure. If external pressure is more, compression work. External pressure more means dP should be positive. If external pressure less than internal pressure means we have expansion work. So for this, dP should be negative. So the value of external pressure is internal pressure plus minus very small infinitesimally small change in pressure. So this. Now therefore look at this, using this in equation A. So work done isothermal reversible is equals to Pi plus minus dP into dV. So we can say this is minus Pi dV minus plus dP dV. Now look at this. dP is a very small quantity, dV is also a very small quantity, so the product of two small quantities will be a much smaller quantity, so we can easily ignore. So this is approximately equals to minus P internal into change in volume. So this is product of two small quantity which can be ignored. Product of two small quantities will be a much smaller quantity which can be easily ignored. So we can say work done isothermal reversible is approximately equals to internal pressure into change in volume. Now we will define this internal pressure. Look at this. For an ideal gas, Pi is equals to nRT divided by V, because we have PV is equals to nRT, which is ideal gas equation. So therefore, replacing the value of Pi in this equation, we get work done isothermal reversible is equals to minus nRT dV by dV. Now, since reversible process means the process which is taking place in infinite numbers of states, so the net work done should be integration of this value from Vi to the V final. So we have to integrate the work done at each and every infinite state. So this gives you the resultant work. Now this is the process taking place at isothermal constant temperature. So N is a constant, R is a constant, T is a constant. So this can be taken outside this integral. So therefore, work done isothermal reversible is equals to minus N RT Vi to Vf dV upon V. So this value is equals to minus N R T ln V final upon V initial. So this is the final expression of work done isothermal reversible process. This is isothermal reversible work done. The same equation can also be written as, so work done isothermal reversible is equals to minus 2.303 nRT log V final by V initial. So this is the final expression of the work done isothermal process reversible involving an ideal gas. So this is natural logarithm, this is logarithm with base 10. So the relation between these two is ln A is equals to 2.303 log base is 10, A have a base is exponential. So this is natural logarithm, this is logarithm with base 10. So this is the relation between this change in volume and the work done. So if you look at this equation very carefully, we have this equation, let this be equation C. If you look at this equation C, now look at this. If this ratio is positive, greater than 1, Vf by Vi is greater than 1, that means if the final volume is greater than initial volume, that means there is expansion work. If this ratio is greater than 1, work done comes out to be negative, that is work done by the system, that is expansion work. If the ratio is less than 1, means initial volume is greater than the final volume, that means we have a compression work, then this logarithm of this term is less than 1 to minus, so minus minus positive, so work done is positive. system के ऊपर surrounding work है, work done on the system, that is compression work. So therefore look at this. If Vf greater than Vi, initial volume is less than final volume. So we say this is expansion process. If this expansion process So ratio greater than 1 is log of this term is greater than 1 positive. So work done is negative. If work done is negative, then this is known as work done by the system. Final value greater than initial value. Ratio is greater than 1. Log of something greater than 1 is positive. So the work done comes out to be negative. If initial volume is greater than the final volume, that means we have compression work. So for this compression work, the ratio is less than 1, so log of something less than 1 is negative, so this comes out to be positive. So work done is positive. So work done positive means work done on the system. So this is how we use this minus to satisfy the convention of work. Now look at this. For an isothermal process involving ideal gas, we have, look at this, PI VI is equals to PF VF. So therefore VF by VI is equals to PI by PF. So in this equation, the ratio of VF by VI can be replaced by P pressure ratio. So therefore work done isothermal reversible is equals to minus 2.303 nRT logarithm of PI by PF. So this is reversible isothermal work done involving ideal gas in terms of pressure. This is in terms of volume. So again, in this equation, look at this. If PI is greater than PF, if there is a decrease in pressure, initial pressure is more, final pressure is less. If PI is greater than PF, that means there is an increase in volume. Volume increase. So if there is increase in volume, that means that is expansion. So expansion, so work done is negative, work done by the system. If initial pressure is less than the final pressure, there is increase in pressure. So if there is an increase in pressure, then volume has to decrease. So decrease in volume means we have compression work. So if there is a compression work, now look at this. This ratio is less than 1, so log of something less than 1 is negative, so this comes out to be positive. So work done comes out to be positive. If work done is positive, we say this is work done on the system. So this isothermal reversible work can be expressed by this equation, minus 2.303 nRT log VF by VI, or minus 2.303 nRT log P by PF. Now this being work done is measured in terms of joule. So R must be in terms of 8.314 joule per Kelvin per mole. N is the number of moles. T must be temperature in terms of Kelvin. So this volume ratio, both the volume should be in terms of same unit. Again, pressure must be in terms of same unit. So this is how we define reversible isothermal work done. Now, for this isothermal process, the work done can be defined for an irreversible process, means in which the change is finite and this is taking place in a particular direction. So we have this irreversible process. So work done isothermal irreversible process. So we define this work done as minus P external into change in volume, because irreversible process change must be finite. Therefore, look at this, we can say, so work done isothermal irreversible is equals to minus P external, V means V final minus V initial. That is final volume, this is initial volume. So this is the external pressure. Now look at this. This irreversible process can be defined under two headings. First one, expansion against a constant external pressure. Work done irreversible expansion against a constant external pressure. So for this, look at this. Work done isothermal irreversible will be equals to minus, because expansion is carried out against a constant external pressure. So P external V final minus V initial. Now this process takes place till the external pressure and the internal pressure both becomes equal. So for an ideal gas, this can be written as minus P external V final, that is nRT by P final, because P is equals to nRT, minus nRT by P initial. So nRT is a constant, so we can take out minus P external 1 by P final minus 1 by P initial into nRT. So if the initial and the final pressures are given, then we can use this equation. Now this expansion will stop when the final pressure equals to that of the external pressure. So this is for irreversible expansion against a constant external pressure. Or we can also define this irreversible work for a free expansion. That is free expansion process means expansion of gas in vacuum. So we have a vacuum in which there is no gas, so we are expanding this gas into a vacuum. So if the gas is expanding in a vacuum, the opposing pressure or the external pressure comes out to be 0. So P external is 0, because we are expansion showing of this expansion, or we are just releasing this gas into a vacuum. So the other container contains no gas, so the opposing pressure will be 0. So that is P external is 0. So if P external is 0, so work done will be defined as minus P external into change in volume, so this comes out to be 0. So if this is the work done expression, then we look at this from the first law of thermodynamics. We say for isothermal process, delta U is equals to 0, Q is equals to minus work done, which is equals to 0. So work done is 0, means Q is equals to 0. So look at this. For this free expansion process isothermal, delta T is 0, change in internal energy is 0, Q heat involved is 0, work done is 0. If all this parameter is 0, then delta S enthalpy change will also be 0. All the parameters will be 0 for this free expansion process involving ideal gas under isothermal condition. So look at this. This is how we define the work done for an isothermal, reversible and irreversible. Now, once we define this expression of work done, we can easily define what is the expression for the heat. Because for this, look at this isothermal process, we define Q is equals to minus of work done. So therefore, work done reversible isothermal, this is defined as minus 2.303 nRT log Vf by Vi, or minus 2.303 nRT log P initial by P final. So if this is the expression of work done, then look at this, what will be the expression of Q? Q will be just negative of this work done. So therefore, the expression of Q, heat involved during the reversible isothermal process, will be equals to 2.303 nRT log Vf upon Vi, or 2.303 nRT log Pi by Pf. So similarly, look at this. If this is the expression of work done, we can say that work done is minus of Q, so we'll minus comes out to be plus. So from this expression of work done, we can also define what is the expression, or we can also calculate the heat involved in this reversible isothermal process. Now this work done is defined as the area under the curve. So graphically we can also define this work done. So let's see how we can define this work done graphically. This is pressure, this is volume. This is suppose compression work. So this is for a reversible process. So this area under the graph, this area under the graph, this represents the net work done. This is net work done. If the process is reversible, means there is a continuous process. But if the process happens to be irreversible, this is pressure, this is volume. So this total area, because in each and every step there is a finite change. So this total area is the net work done. So simply saying work done is area under a graph. This is irreversible process. This is reversible process. This is irreversible process. We are having the compression work of compression, because we are decreasing volume, so this is compression work. We are going from this to this value. So this is simply what I am going to say is, when we have the graph, then from the graph also we can define what is the net work done. So total area under the graph represents the net work done during the process. So if you look at this, during this reversible process, we are integrating the process from initial to the final value, and this reversible process represents the maximum work done, because at each infinite steps we are changing the process by infinite numbers of steps, and this reversible work always represents the maximum work. So whenever the question says the maximum work, that means the process comes out to be reversible. Why? Because at reversible process, the process is taking place at infinite numbers of steps, and at each and every step, infinitesimally, we are adding the values of infinitesimally small steps, and that represents the maximum work. So reversible work is always the maximum work. So look at this problem. We have an ideal case. So this ideal case, this is argon. 10 gram of ideal case argon is compressed reversibly at 27 degrees centigrade. So question says this is a reversible compression process of an ideal case argon whose mass is 10 gram at constant temperature, from initial volume of 10 liters to the final volume of 5 liter. If the gas constant R is 2 calorie per Kelvin per mole, then find the values of heat involved, work done, change in internal energy, change in enthalpy. So if question clear says temperature is constant, so temperature constant, this value is 27 degrees centigrade, or we say this is 300 Kelvin plus 273. Process is reversible. We have a reversible process. So this is isothermal reversible. Isothermal and reversible process. So first thing, for this isothermal reversible process, delta U will always be 0, because for an isothermal process involving ideal gas, delta U is always 0. So we have the values of delta U, because for an ideal gas, U is a function of temperature only. So if temperature remaining constant, delta U will always be 0, that is change in internal energy will always be 0. Now we have look at this. We have this expression of work done. So work done is minus 2.303 nRT log Vf by Vi. So we have minus 2.303 n. Number of mole is mass by molar mass. So we have 10 by 40. Molar mass is given as 40. R is given as 2. Temperature is 300. Logarithm of V final. V final is given as 5. V initial is given as 10. So we have 5 by 10. So look at this. This ratio is less than 1. So log of something less than 1 is negative. So this is positive. So work done comes out to be positive. So this is compression work. So system के ऊपर surrounding work है. So work done should be positive. So to find this value of, you have to use the log table. Now this is work done. Then look at this, we have to find the values of Q. So for this isothermal process, Q is equals to minus of work done. So therefore Q is equals to minus of this value. So this is some, suppose this is some positive A, then the Q will be minus of A. So we have to find the values of Q. Now we have to find the values of delta H. Now the process is isothermal. There is no change in the number of moles of gas, then delta H will be also 0. So this is how we find the values of the various parameters for a reversible process. So coming to the second problem, we have 1 mole of an ideal gas undergoes reversible expansion, isothermal reversible expansion from initial volume Vi to final volume, which is equals to 10 times Vi. During the process, work done is 10 kilojoules. So this is expansion work, so work done should be negative. If the initial pressure was 10⁷ Pascal, then what is the final pressure and what was the initial volume? So question says temperature constant, process is reversible, work done is minus 10 kilojoule per mole, because this is expansion work, so work done by the system on the surrounding, because there is increase in volume. So therefore look at this, we have to find the values of Vi, we have to find the values of Pf. So now look at this, work done isothermal reversible process, the value is minus 2.303 nRT log Vf by Vi. Then we have minus 2.303 nRT log Pi by P final. So question clearly says the work done is minus 10 kilojoule. In this case, temperature is suppose certain temperature T. Then we have to find the values of the final pressure. Initial pressure is given to you. Temperature is not mentioned. Simply say this is an isothermal process at temperature T. Volume, initial final volumes are given to you. Now we have to find the temperature at which the process is taking place. Once we know the temperature, we can find out the values of Pf. So use this equation again. So from this equation, we have work done, we have Rn constant, this is given to you, this ratio is given, so we can find the values of temperature, what was the temperature at which the reaction, this process has been taking place. So once we know this, we can easily define the values of Pi or Pf. So therefore look at this, for this isothermal process, therefore look at this, Pi Vi is equals to Pf Vf, isothermal process. So therefore look at this, Pi by Pf is equals to Vf upon Vi. So Vf upon Vi, that is 10 Vi by Vi, so Vi cancels out. So therefore P final is equals to Pi into, this is Pi by Pf is equals to 10. So therefore Pf is equals to Pi by 10. So Pi is 10 to the power 7 divided by 10. So this comes out to be 10 to the power 6 Pascal. So if suppose we have to find the temperature at which the process has been taking place, we can also use this equation to find the values of temperature. So we have this pressure. So this is initial pressure and the final pressures. Now we have to find the values of this initial volume. What was the value of this initial volume? So from this ideal gas equation at constant temperature we find the values of final pressure. So we have looked at this equation isothermal 2.303 nRT. This can also be expressed in terms of Pi upon Pf. This is pressure ratio. Now for this process we have ideal gas equation. So ideal gas equation says pressure final volume final is equals to N R T. So we have pressure volume and RT. We can define temperature from this equation. So work done isothermal, this ratio is given to you. We have to find the values of temperature here. So therefore look at this. Vf is equals to N RT by Pf. We know the values of Pf here 10 to the power 6. Now what is the value of T? Look at this. Work done is minus 10 into 10 to the power 3 joule is equals to minus 2.303. R is 8.314. N is 1. So we have 1 into log of Vf is 10. Vi is 1. So log 10 is equals to 1. So this is 10 to the power into temperature. So therefore temperature, so this is 10 to the power 4 is equals to log 10 is 1. So 2.303 into 8.314 into temperature. Therefore temperature is equals to 10 to the power 4 divided by 2.303 into 8.314. This is temperature Kelvin. So we have this temperature here. We'll use the values of temperature. We have the values of final pressure, that is 10 to the power 6. So we'll find the values of Vf. Once we know the values of Vf, Vf is equals to 10 times Vx. So let's suppose this is equals to x. So therefore look at this. Vf is equals to x is equals to 10 times Vi. So therefore Vi is equals to x by 10. So this is how we define the initial volume, provided we know the conditions in which the process is being taking place. So look at this question. 5 mole of an ideal gas at 298 K are expanded isothermally from an initial pressure of 4.053 into 10 power 5 Pascal to final pressure against a constant external pressure of this value. Calculate Q, W, internal energy change and enthalpy. So question says against a constant external pressure. That means the process is irreversible. This is irreversible isothermal process. The question clearly says against a constant external pressure, that is irreversible process. So for this isothermal process, first thing is delta U is equals to 0. Now we have to find the values of work done. So work done is minus P external into change in volume. So we say this is minus P external final volume minus initial volume. So we can express this final volume, initial volume in terms of initial and final pressure. So therefore look at this minus P external 1 by Pf minus 1 by Pi N R T. So P external is 1.013 into 10 to the power 5. Final pressure is 1.01 into 10 to the power 5. Initial pressure is 4.053 into 10 to the power 5. N is 5. R is a gas constant. T is 290. So we have this work done. So this is minus 1.01 into 10 to the power 5. 1 by PF is again same, 1.013 into 10 to the power 5. So 10 to the power 5, 10 to the power 5 will cancel out. So 1 by 4.053 into 10 to the power 5 into N. N is 5. R is 8.314, temperature is 298. So this must be in terms of joule. So this is how we use this work done. So suppose this will have certain value, so we can just cancel out 10 to the power 5, 10 to the power 5. Okay. If this is work done, then what is the value of Q? So from this first law, work done and Q is related as such. So if suppose this is sum minus A, then therefore Q will be equal to minus of minus A, that is plus A. Now this gas undergoes expansion from this initial pressure to the final pressure without changing the number of moles of gas. So therefore delta Ng will be 0. If delta H is 0, then delta H is equals to delta U. So delta U is equals to 0 means delta H is also 0. So for this process, delta H and delta U will be equals to 0. Work done is this we have. Once we define this work done, we define this Q, that is heat involved in this reversible isothermal expansion process. So coming back to this question says a gas expands from initial volume of 3 decimeter cube to 5 dm cube against a constant pressure of 3 atm. The work done is used to heat 10 moles of water at initial temperature of 290 Kelvin. Calculate the final temperature of water if the specific heat capacity of water is 4.184 joule per gram per Kelvin. So we have n moles of ideal gas changing from initial to final state at a given temperature against a constant external pressure of 3 atm, and during this process some work is done, and that work is used for heating water, 10 moles of water, which initial temperature was 290 Kelvin. So therefore temperature remaining constant. So we have isothermal, irreversible process. So therefore work done is equals to minus P external into change in volume. So therefore look at this, work done is minus of P external change in volume. Volume is 3 decimeter cube to 5 dm cube. Then external pressure is given as 3 atm. So work done being measured, now look at this is measured in terms of joule. So work done must be expressed in terms of joule. So look at this is atm, this is decimeter cube. So we can express this in terms of liter atm. So we have to convert this decimeter cube into liter. So look at this, or we can do, look at this, atm can be converted into Pascal. So we have, look at this, 3 atm, 1 atm is equal to 1.013 into 10 to the power 3 Pascal. Delta V is 5 minus 3, so 5 minus 3 decimeter cube, decimeter 10 to the power minus 1 dm cube. Hmm. So this is Pascal standard unit of pressure. This is meter cube. So we have this value. So this is minus 3 into 1.01325 into 2 minus 3 plus 3 will cancel out. So this is Pascal meter cube. We say this is Joule. So this much work is done in this irreversible isothermal process. So look at this, 1 atm is equals to 1.013 into 10 to the power 3 Pascal kilopascal. So this is the total work done for this process. So, sorry, 1 atm is equals to 1.013 into 10 to the power 5 Pascal. So this is the work done during this irreversible isothermal process. This much Joule is done. Now the question says this work done is used to heat 10 moles of water whose initial temperature was 290 Kelvin. So we have 10 mole of H2O is to be converted into 10 mole again. Now initial temperature was 290 and what is the final temperature? Now, the heat supplied for this heating is equals to the work done. Question clearly says work done is used to heat these 10 moles of water. So therefore, look at this. We have an equation of heat in terms of specific heat capacity. So Q is equals to M into specific heat capacity into change in temperature. So this Q is equals to work done. So we have this work done. So this is the heat that is work done which is used for heating this. So Q is equals to this value. So minus 3 into 101.3 into 2 into 10 to the power 2 Joule, which is equals to, now look at this, this specific heat is defined as Joule per gram. So we have to define this 10 mole in terms of gram. Mass of 1 mole is water is 18. So mass of 10 mole is 10 into 18 gram per mole into S is, what is S? 4.184 into final minus initial temperature. So therefore look at this. So TF minus TI is equals to minus 3 into 2 6. So 6 into 101.3 divided by 180 into 4.184. This is the difference in temperature. So therefore the final temperature is equals to initial temperature minus 6 into 101.3 divided by 180 into 4.184. Initial temperature was 290. This was initial temperature which was 290. Then this value moles of water that. So this is plus. So plus 6 into 101.3 by 180 into 4184. This must be in terms of Kelvin. So this is how we use the equations to solve the various types of problem. So work done is used for heating this water whose initial temperature was 290, and so water is being heated. So the final temperature should always be greater than the initial temperature. This is 290 plus something, so this is the final temperature. So this is all about reversible, irreversible isothermal work done. Okay.